So this is a bit of a, should I already record? Actually, I'm not sure if I'm recording already. Yes. This is a slide that comes back over and over, and part of the reason is because we're looking at different portions of it, but I always want to put it in the context of itself so that you can see how much you're covering. Next week, we're going to be looking a little bit more about pattern completion, but you've seen quite a bit already previously about contrast enhancement via lateral inhibition. Next week, again, we're going to see sequence generation. You've already seen something about the extraction of motion from moving images via the high shot detector with delays and possible filtering, sensory motor control. And also next week, we're going to look into memory with attractor dynamics. But I guess that the intuition, I have to work no longer on the intuition that pattern recognition and hierarchies are inextricable. I hope that Josh gave you a substantial amount of confidence in the idea that it looks like the brain is breaking it apart first, joining locally the information to extract luminance, and then to extract edges, and then to extract corners, and so forth and so on. But I want to overplay and emphasize how is it that hierarchies build invariances. And I'm going to talk a little bit about invariances again. I think that we already mentioned them swiftly in the first lecture and in another moment, but it's also a concept that I think must return often, because that's the essence what there is in a cognitive type problem. So the invariance is that what defines a problem, in a sense, the behavioral invariance. And so the kinds of hierarchies we have in the brain, I mean, we've measured them from the retina on the left side here. We have from the retina to the thalamus to V1, V2, V4, TEO, temporal extrastriate orbital cortex, and TE. So the ventral pathway, basically, so we're going temporal, and then dorsal pathway. So indeed, this is then the analysis of space and action planning. But up to V4, they share that. And one of the things that I wanted you to attend to, and I don't know how much emphasis Josh laid on it, is the fact that the receptive field size changes quite a bit along this processing stream. I don't remember if he has this slide. But yeah, in the photoreceptor, you have these features, RGB, and gray values for the rods and cones. That's it. And the very high resolution, because it's, for every rod or every cone, you will be extracting the value there. Also very noisy, because it's a quantum process, and every single receptive field is giving a bit of a fuzzy feeling there. It acts stochastically. It does measure light and converts into frequencies, but it's fairly unreliable. The ganglion cells in the LGN will already start to look at color opponency. So the idea that it's relevant to know where something is and the color contrast that it might have, but also fairly small in terms of receptive field size, because it's combining just the local environment. So have to think about in the back of your mind, what is the size of the receptive field of the retina that is required until you can compute an on-off procedure. So scale, spatial scale. You need at least a bunch of surrounding neurons on top of a center neuron. And how big is it? How many micrometers? So this is actually relating directly to a certain visual angle. So what, the eye is a ball, it has a lens, and it absorbs the world according to angles. So you can measure the visual angle and the receptive field in terms of the visual angle, and then you can relate that back to the size of the network that you have at the level of the retina, the size of your pixels. These discussions have been put forward. It's actually another interesting project to relate the size of receptive fields with the kinds of categorization problems that you can solve. Then you have in V1 formed the standard model of orientation selectivity. By the way, I remind you that I mentioned that if you think I'm going too slow, then you can continue pressing play. I'm trying to create a different angle from what Josh had, but playing on the same general idea. But if it's going slow, just let me know. Then you have complex cells that are looking more into texture, and their receptive fields are substantially bigger. In V4, we're already looking even for curvature selectivity. So this is a feature that I know we talked about before. But these are very fundamental with respect to how many pixels do you need to see the entire curvature. And so not only you have a fairly sizable receptive field, but also it's mostly relevant close to the fovea. So the receptive fields exist in this in relatively close to the center of the fovea. And then you, after having extracted all these features, you can recombine them in ways to produce simple shapes and elements, and also more complex feature configurations. And you also see here in the ventral pathway that you have elemental combinations and more coarse level, larger scale combinations that are extracting things that are even small, either small, like detailed shapes, like particular contours of objects, or complex feature configurations, like how the eyes are with respect to the face, right? So you take mushrooms, the eyes start to move. Where do they move in your brain? Not where you're looking at the small features, actually, also the small features, but the general a perturbation at that level will create a shift of large receptive fields. There's data to this, and this is a comparison between V1, V2, and V4 with respect to the sizes of their receptive fields. And not only the size of the receptive field, but where the receptive field center is with respect to the fovea. So you can then see this procedure. I guess the best representation of this is the one here on the top right side, where you see an imagined configuration of the retinal resolution. It's radially, you guys, I think you can probably figure out why it's radial. It's because it's the retina. The retina is a disc, so these receptive fields will have this radial idea. But it's just a representation of the size of the receptive fields and how they change as you go down the processing hierarchies. And the essential task of hierarchies is to create invariances. I will try to get this word to you once again, and we'll work on this. It reappears in multiple analyses of neural networks, and that's why I want to solidify it. The definition that I'm using here is the definition, the physical definition from Emily Noether, who was a great scientist who she's shown that whenever there's symmetry, there's invariance in a mathematical sense. But what we mean here by transformation more generally in the context of the sensory motor system or the sensory system is the ways in which something can change and keep something else unaltered. So, for example, we talk about shift invariance. This object here, in any position that I may shift in my visual field, doesn't change. If I rotate it, however, the overall shape will change, more rectangular. This is a circle. This is an oval. So you have some transformations destroy certain invariances. So in this case, this transformation does not destroy the circularity. Shifting is not destroying the shape, circularity. Rotating the object is destroying the shape. but none of them are destroying the essence of the object. So, color. No, I mean, you can change color and then you would not change the shape. And so these are dimensions along which you can transform something, an object, and keep certain properties, other properties, abstract properties unchanged. So the meaning of an object, for instance, is invariant with respect to multiple variations of the stimulus. And these variations, you should be thinking about dimensions of variation, things that you can smoothly change in the object, in the stimulus, that will keep things unchanged. Now, it's a very abstract concept, and I'll try to give you a couple of examples, but the idea is that you should step back from what you're looking at and imagine, in which ways can I change this and keep it the same? Great heuristics when you're making experiments, for example, in the perceptual space. Because when you're making an experiment and you want to present something to a cat, you want to keep certain things unchanged. For instance, you want to keep the orientation of a bar unchanged, but you might be wanting to change the width of the bar. And if you change the width too much, then that orientation starts to actually activate the receptive field. Hence, that a receptive field is not, or that dimension of change has destroyed certain invariant response properties of the receptive field. The receptive field defines what it's looking at. So trivial low-level examples would be contrast, luminance, rotation, scaling, and some distortions. But we can also talk about time invariance. You recognize a word the same way across time, mostly, unless someone told you to think about something else when you think about that word. So priming, if I tell you Elvis and I tell you King, you have a different picture than if I tell you Queen and then if I tell you King. So it's a different. Surely some interpretations are not time invariant, but you do have that invariance of the spectrograph. The word king was absolutely the same if you have a frequency decomposition of that word. And to play on these invariances, this idea that the brain instructs invariances, even like very high-level shaped invariances, was building up from the work by Hubel and Wiesel. And they were seeing that the brain even does this sort of, like this is an old paper, where they were trying very abstract shapes, and like what kinds of receptive fields does the brain have a receptive field for? I bring you back to the idea that this is all very subjective because the presenters decided, okay, maybe like, how does it act to shapes? And so the shape space is very large. There are many possible shapes you can present. But in this particular case, they're measuring some, a circle with another circle, a little nipple on the circle. And there seems to be a neuron in the brain that is very happy about seeing that particular nipple. Or maybe it's an evolutionary cell, but if it's inverted like this, it's not so good. That cell doesn't see it. It doesn't like the circle. It's not only the nipple, it's basically the entire breast, right? So apologies for maybe some people find this inappropriate. I mean it objectively. So the objects that we see, like in the brain, will represent certain abstract components, even though you have certain variances on it that try to capture some invariance. And the response on these neurons are going to be really graded. The ones here in the bottom are also really quite interesting. I mean, if you exaggerate that feature on that shape, this protruding feature in the shape, you get less activation than if you actually squish it, although you get zero activation with a circle. This is all very weird, right? And so this is precisely why I'm showing you this, because you have graded activation of multiple cells in the brain that are representing abstract shapes, and you can actually inquire on them, what are they doing. But one thing is clear. There's a bit of graded response in multiple cells representing the feature extraction even at higher levels. Another thing is very clear, that the receptive fields in the brain, even though we talk about, like the exact position in the brain, the types of shapes that we will see will be represented in different groups in the brain. So not exactly in the same place. So if you see here, for example, shape 1 had most active receptive fields in the infratemporal cortex in these 3 positions. This is a 1 millimeter patch of a monkey brain. So you can see that preference for that neuron exists in different parts of space, which is giving the idea that it's graded and it's distributed. Parallel distributed processing is the word that I want to create from this sequence of slides. PDP. PDP was one of the foundations for the rediscovery of neural networks in the 80s, proposed in this form by Jake McClelland. Write his name here. So Jake McClelland. He's still between us. He's an older guy, but he has actually a nice podcast episode where in the Brain Inspired podcast. Where he discusses his original intuitions about parallel distributed processing, also thinking about where AI is going. But what his general idea was, okay, well, a neural network is perfect for this. You know, that's exactly how a neural network encodes stuff. We're going to talk about how to train those things in a moment. But one way in which you can train them is by having learning, by presenting patterns with statistical regularities. You will have distributed receptive fields like this if you present the patterns in different places of the receptive field. So even with unsupervised learning, you already create graded and distributed representations of abstract ideas that are implied by the sensory stream that you produce. And you have these extremes. I don't know if Josh mentioned this particular paper to you, which I think is very illustrative of the overall idea. So invariant visual representation by single neurons in the human brain by Kian Quiroga and Christoph Koch and Fried. This is the infamous and now famous paper where, did you see this picture before? Okay, everybody remember it? Some more than others. So the ones that remember, okay, so anyone doesn't remember, can you say no if you don't remember? Okay, so everybody, 100% of the sample remembers. But I'll just mention one thing. You guys, like that, definitely remember, you certainly have Jennifer Aniston cells. The probability that you will find a Jennifer Aniston cell is very small. This is one of the accomplishments of this paper, to show that there are very few cells that actually can do this representation probabilistically. And in fact, the main argument in this paper is not only that there are neurons that are invariantly representing very complex concepts, or even multimodal concepts. I don't know if you've seen this one. So this is Halle Berry. I think that he did show this because I provided him with my reference slides, and so I think he did, right? But in any case, so like these are higher level concepts that involve not only the face of a person, but also the name. So the name being spoken. So the same neuron would respond to the name being spoken and to the face of the person and to the name being read. And it wouldn't be, not to John McCain, thankfully. But probably the person did have a John McCain neuron too, because it's back in the day. Invariant recognition is being assembled. So how it's being assembled, and you already know it's hierarchies and it's neural networks, and you have layers and layers and layers. Let's now talk about constructively how these things come to be. One more example of invariant pattern recognition, which is not so sharp, but is also interesting. So here you have the activity evoked by the Sydney Opera in this neuron. This paper is in the Journal Club. This paper has an interesting statistical analysis of the likelihood of finding a neuron with the Sydney Opera cross-correlating it with the idea that that neuron must be unique, because you don't have that many neurons that can represent every named thing out there. So there actually have to be few representative neurons. This idea has been strongly opposed and contended with in more recent literature, but surprisingly, the papers that tried to break it didn't quite address the main statistical arguments in this paper. So if you're curious about this, I definitely recommend to look not only into this paper, but into the follow-up or invariant representations. It's a critique. Both of the papers are going to be in the treasure chest. I call it the treasure chest, the article bunch that where many of these ideas sprout from. I don't suppose that I need to tell you anything about regression and classification, do I? You already know all of this. You knew it even from before. And probably now you also know how you make them with neurons, because you watched 3 Blue 1 Browns video. But just to refresh your memory, I want to share with you quickly here my iPad drawings, and then we're going to go into linear classification and how to assemble this, because this is now the essence for today. Okay. So let's just think about how a neuron can create regression to begin with. So a regression neuron is creating a prediction from a variable X. It's creating a variable Y. And you can have neuron, one of the neurons, wait a second, why are you not drawing? Hey, this layer is hidden. Okay. So from neuron 1 to neuron 2, you can create a prediction via a certain weight, right? So this would be like a trivial function in which y equals w times x. And you can also create a shift of that function by adding a bias or a theta. In general, if you don't create the bias, then you will have something that goes through the origin. But you can then, this neuron can then relate input to output. In this case, it's actually suppressing its output the more input it gets. So it's an inhibitory neuron. I hope you can read this from the weight function that is represented in W. A classifier neuron can also work with a single input, but I wanted to show you in the context of linear classification or linear separation of spaces. So a classifier neuron is, you have already basically looked into classifier neurons. The do-it-yourself receptive field is nothing but a classifier neuron that takes 9 inputs and classifies the output as a single orientation. And here you will have a certain function f. Ooh, it's not transparent. I think I might have to actually, how do I opacity? Which will use the line to distinguish two sides of the two-dimensional space. The positive side and the negative side. Here's a nice little question for you. So this function f is our friendly, it's very similar to our friendly Heaviside function, but it's not identical because it's a sign function. It says if something is smaller than 0, we're going to return a -1, and if something is larger than 0, it will return a 0. I challenge you in your heads to plot this function in your brains. So this function f, as I've drawn it now, is responding with a, no matter what the input is, if it is negative, it's going to return a -1. And if it is positive, it will return a +1. So this is input, and this is the output of the function. Hope that this is trivial. So if you apply this function to the operand of a neural network, which is basically combining the activation of two different neurons, A1 and A2, you basically are separating the positive from the negative side of the world as such. So I'm trying to draw here. Right? So this function f from this unit has this output. And when it operates on an input space formed by two neurons, A1 and A2, it will distinguish the space between the left and right. Very abstract, but A1 and A2 could have tuning curves for stuff, for Jennifer Aniston and Halle Berry, and maybe so maybe you have a classification function. No, actually, but let's think about like a bit easier features for this. Let's say yeah, so a nice example. Do you guys want to come up with example for change? I mean, like, my analogies are always so terrible that I sometimes want to refrain from doing them. So the idea here is that you have to find a space between two input dimensions that are represented by neuronal activities that would be classified in this way. So that is, when you have very large activations, or when you have activations as such of A1 and A2, you would classify as yes, and activation as A1 as A2 is smaller than the separating hyperplane, you would classify as no. Anyone can come up with an idea. Keep on thinking as I explain, and then if you pump it to the chat, we're going to talk about. Obviously, there's millions of different ways to do this. But this is the fundamental operation of classification in the case of data sets. And the pluses and minuses here that I've outlined are nothing but, are nothing but the individual presentations of stimuli. So each of these would be a stimulus. Let's give them a green color so that they're neutral. So we start with, we would like a network that is, or a neuron, that is able to distinguish between the negative signs and the positive signs. And each of them is a data point. So the entire data set is constituted by, say, 11 data points, each of which with two dimensions, A1 and A2, and we would like to create a classification, the best possible classification, a separation between these hyperplanes such that when you present a single stimulus to this network, got a better color, any new stimulus to this network could be here, the network will answer you, positive or negative. New examples that we haven't seen before. Right, so linear separation, that's the fundamental idea behind it. And each of these examples is basically a combination of A1 and A2. I don't know if this color is the best chosen color in the world. a particular instance, a particular set of co-activations between two neurons. We think about the small network first to get a hold of this. I want you to understand the operation of the sign function on the separating hyperplane defined by the weights of the network. And I want you to ask you another little thing. So you didn't come up with any examples for A1 and A2 yet. We can discuss more concrete examples as time progresses, but just keep in mind that we're talking about two features that are in principle independent and nevertheless can be combined via a neuron in this fashion. Question: what are the weights? Oh, sorry, I screwed the question. What are the intercepts of this separating hyperplane? Notice, I am talking about this function f that is distinguishing the positive and the negative sides of this operand that is represented by the activities of the input neurons times the weights that are multiplied by. So what are the intercepts? I'll give you a hint, and then I'll give you 5 minutes to think about it. It's going to be, yeah, we're only going to do 2 more things until we go to the next part of the lecture. But notice, this is the operand that we had before. And so the question is, when is it 0? And when it's 0, we have that line, the green line. Dot product. This is the slope of the function. This is the relationship between the activity of neuron 1 and neuron 2 as a function of weight 1 and weight 2. So you don't need most of this to really figure out what these intercepts are, but it's an important linear algebra skill that you must acquire to be able to look into a graph and have a sense for what the intercepts are. I'll give you the answer and then you will think about why it is. Go back to the video afterwards and then think about it. If you have difficulties, ask another one of your colleagues that knows much about. Great time for breakout rooms. Let's have a 4-minute discussion whether everybody sees where this is coming from. I'm going to copy and paste this particular graph onto our chat so that you have access to it when I do the breakout rooms. And the question for it is very simple. Can you understand where these intercepts are coming from? Because it's a fundamental linear algebra operation, very simple, that I'm sure that you will find colleagues that can explain to you if you don't. I'm actually curious how it's going to happen on the output. It's also a little probe on my side. Do you guys understand? So when each is activated individually without it. Yes, but I'm not abstractly concretely. That's the question. It was finding an example for concrete features that for neuron 3 that combine A1 and A2. Bracket. We're going to go for a breakout room, and in the breakout room, you will look at this graph and discuss with, or work by yourselves. Discuss with the colleagues if the colleagues do understand. Okay, so I'm not going to go into the breakout rooms. You will have 5 minutes to discuss this, and then I'll bring us back. You know what you have to do? So with 28 participants, I'll create 5 breakout rooms. And I'll let to choose the rooms. How about that? I'll let you choose the rooms, and then you can come to the person that you think is most likely that is going to be able to help you if you didn't quite get the point. But before I do that, I actually have to copy the figure into the chat. I don't know if I can do it this way. So does it let me? No. Just a second, please. I need to create. Oh, come on, Zoom. Give me the chat in the same window where we are. All right. Works out to be a hefty download. It says 6.7 megabytes. Yeah. Why is it so slow to upload? Okay. I'm going to this. Yeah, it has been sent successfully. So you must have been seeing it in your chat. And now we get 5 minutes in the breakout rooms. Let's see where are the breakout rooms. That's not the thing I have to find out. Cool. Open all rooms. You're welcome to self-assign and then see if what I want to learn from you is are you able to tell what the intercepts are just from the neural network equation? You have to assign yourselves. You can start randomly. I can also do that for you. What was that?
How does it work on my server?
I don't know.
You should move back to the Zoom window, and then there should be a self-assigning thing. No?
No, we can't do that ourselves. I think the host has to do it.
You cannot? Wait.
No, we don't have a button or anything.
Okay, so wait, but some people managed. Some people managed. Jimmy and Sue and others seem to manage. Okay. Okay, let's try it again.
Did you close the breakout room?
I did. I'm going to open it again with calculating that, but it now has 30 seconds until it was going to do it for us, so we have to wait. Great. 24 seconds until it can create another room. I cannot simply kick everybody from the rooms. Yeah. So what did you see, by the way? So because here from my end, it seems like it's same.
There was nothing. Like nothing changed, at least for me.
I think it's probably some sort of subtle change somewhere. Because so I can recreate the rooms, and I'm going to assign automatically then to avoid confusion. So
and below where you have the participants chat, etc., there was a small icon for breakout rooms, and if you click on it, then you could join the number.
Yeah, I thought yeah, something subtle. No, yeah, that's what I thought. But I'm going to self-assign so that we don't lose more time. So now it's 10:59. In 5 minutes, I'm going to bring you back. So again, it was easy enough, huh? Easy enough. But the reason why I've asked you to do it, and I actually want to first tell me in the chat before I go forward, how many of the groups have consensus in which everybody goes, yeah, I get it, obviously as a X and Y plane. I mean, like, you know, the Descartes plane, he's invented it 300 years ago. We all get it. Yeah, we answered your survey monkey. It's obvious. How many of the groups have a full-fledged one? So if you would kindly speak for your group. You all did not get it. Okay. Okay. So, but you can draw a line in a plane, right? And so, I'm not going to explain it. I'm just surprised. So I'm going to say, you know, I'll find you a page right now on the internet that says how to find the intercepts of a line. So the point is that the intercepts of a line are the weights of the network for the separating hyperplane. So just by looking at the weights, you can see it immediately. So intercepts of a line. There are about 8 million results. So if you didn't get it, I definitely recommend you go ahead and try. Now we have one group that did get it, the other group that did not get it. So please, the other groups, will you please speak up? Yay! So we have, we're going. So if you didn't, that's something to get in the offline. I was actually kind of expecting to have a 80%, I get it, more or less. And for the ones that did not get it, this is an important thing to get, the intercepts of a line. Okay, so it is not from here, but more generally, something that you just, it's the first hit probably is going to give you more than enough information in Khan Academy. But the reason why I'm bringing it over to you here is because if I ask you, for example, in the quiz, to select weights that allow you to categorize a certain data set where I tell you exactly what the X's look like and where things are. For instance, I can say, for instance, that this is 100 and this is 10. Notice that these neurons have different amplitudes, and so the data that you're putting in is very different, and that's why they actually become important. You should be able to find both an orientation of a line given the intercepts, both here and here, and represent them directly as the weights of a network that would be able to classify that via a -1 function. But as I'm talking about it, this is the intuition behind the entire idea from the perceptron algorithm, which is from Rosenblatt in '58. He said, you know, if you give me a network, not with 2 neurons, but with 3 neurons and an output, provided that the data is linearly separable, provided that I can draw a line or a plane, see, and if in 3D, that criterion W1, A1, W2, A2, W3, A3 would actually look like a plane in the space. And then you could separate pluses and minuses in the 3D space, right? So Rosenblatt thought, well, you know, that actually generalizes. If I have a 4-dimensional space, I can I can generate a 4-dimensional plane. I can separate anything from anything else, just as long as they're linearly separable, just as long as I have a well-defined sign, you know, the operand of the sign function, which is a linear combination of the activities of the input for any number here of weights and inputs, just as long as I can define this sign function with a linear operand, I can train a network. I can find these weights here that will distinguish the categories. The first case, the one that I asked you to imagine, is directly from the intercepts, and so this is a possible data set. It doesn't need to be 10 and 100, could be 1 and 1. 10 and 100 makes it a little bit more interesting to think about, not in terms of neurons only, but in terms of linear classification more generally. I'm sure that for some of you this is trivial, but bear with us for the sake of the others. Now, say you start with a random network. What does that mean? That a random network of two weights in this two-dimensional case with two random weights W1 and W2 would, and potentially a bias here. I'll add a bias in this particular case. I also would have to center the data set. But you know, the bias is simply saying plus or minus the intrinsic activity. I guess you already got the point. I shouldn't belabor it. Random weights will draw a line. Random weights with a bias will draw a line. Some position, who knows? So that's going to be the initial line. What, not Rumelhart, Rosenblatt figured out is that you have an iterative procedure to modify the position of that line such that it achieves best possible categorization given new elements of the data set. And the idea that he had is, okay, so what I'm going to do is I'm going to start with a random line, and then I'm going to do the following. If that line is failing to classify one of the examples, I should change the position of that line in the opposite direction of the error that I obtained. So the algorithm effectively is this, and you will be looking into multiple versions of the perceptron algorithm to be able to mull over it later. But the essence of the algorithm is this. A binary classification problem for any number of input dimensions where you have labels -1 and +1, this is the output of your sign function, having parameters W, which is your weight vector, and a decision boundary, which is a line or a hyperplane. So line, 2 dimensions, hyperplane, 4 dimensions. What we do is we start with that random separating hyperplane, and we do the dot product between the input of the, for every single data point, for every single observation, we create a prediction of that sign via the line that we have. So for example, if this is the line we have and we added a new data point here, let me make it a thick data point. If we add a new data point over here, then what should we do to try to create a, to try to bring the separating hyperplane to the right place? Well, we actually want to move this line a little bit. So, because if we just, as it is, if we just give this data point to our sign function, it will actually return a minus because it's under the curve. So we assume that that's where the minuses are. So it should be a plus, but the output is a minus. What should we do with the weights? Well, the weights are actually creating too much negativity. So what you should do is subtract negative from the entire weights. So you're pushing the line towards the positive side. And you might actually be doing this step by step. So you just use the knowledge that you now have to try to shift it a little bit towards your training example. A bit, a learning rate. You don't need to do it all at once. You actually can do that all at once as well for linearly separable problems. But the thing that I'm trying to get here is the intuition. So you do this systematically for every single new example. And so you present a guy, oh, this one actually was classified in the right place already, so we don't need to do anything. So for every new example we do, we shift the line if we need to. So if we present also this other negative example, the sign function will return a negative, there's nothing to be done, and so forth and so on. However, for this negative guy here, we're actually returning positive in this according to assumption, and so it will push the plane back towards it. These guys here are mostly correct. So you see that it's an iterative procedure that tries to modify the position of the separating hyperplane by changing the position of the intercepts. The intercepts are determining where exactly this separating hyperplane will be. And what you can do just by looking here is to, in general, to create a good line that that separates those two planes. And you would know, okay, so here this is the line that I really would like to create. At the start, I mean, so maybe something like this would be a good line, or something like this would be a good line. Perceptron will not, this perceptron algorithm will not create one unique line. It will create a set of possible lines because it's an iterative procedure that depends on the direction of presentation of the stimuli, creating certain variability in the neural network, even though the feature for which it is selecting is the same. The actual algorithm looks algebraically like this. You update W and B for theta based on one data point at a time. The data point has A1 and A2. So if the sign function here, this is the Y, the output of your neuron. Okay, so if the sign function returns positive, you have no loss, hence no update. If the sign function is negative, that means you classified it incorrectly, then the loss is negative, and we're going to add that negative in. If you know, notice that you can, if it is negative sign, the output, if they're basically an incorrect classification, you then go into the other direction via adding a little bit of that output to the input. So it's the output that you're adding to the input. And this is the essential idea in the perceptron algorithm. And you can do this if you, here's another idea for a project. I gave you the DIY, do-it-yourself neurons. And in those, you selected the weights manually. That's kind of like saying that you've created a separating hyperplane directly in your heads, if you actually did the exercise. And so really, that's where it's at. It's at you selecting the weights, or you thinking about a procedure that creates a gradient towards the weights that, when selected, bring you to a correct classification. But this is a linear classifier we're talking about, not an, so I presented a neuron side by side to the linear classifier, whereas the intention here is to say that simple feed-forward one-layer neural networks are by necessity all linear classifier. A perceptron is the algorithm for creating that a proper classification for linearly separable data. What you're going to do in next lesson, if we, or maybe we're going to start even today if we have the time, is to start with where is it? Not maybe. So to play with a playground in which you're going to try to separate data sets. So this is what you will have as both a project for next week and a assignment to get acquainted with. I actually produced a set of questions that you can then research here, but ultimately what you have is a data set of points, blues and oranges, that you want to find a classification scheme for by training it via something like the perceptron algorithm. And then you have data sets that are not linearly separable like this. And I will tell you, okay, maybe if you add hidden layers, you will be able to separate them via the same algorithm that I described a second ago. And so And I haven't explained any of this yet. I'm just saying that this is where we're going. You will then be able to create more of these hidden layers and play with the sizes of neurons, and then interpret these receptive fields of these individual neurons and their combination before and after training. So here in this, what I demonstrating is the ability of networks to classify these non-linearly separable points with multiple layers as well. And I did this on the fly without really even thinking. I'm talking to you as I'm doing it. So I expect you to, after you go through the playground assignment, and next week we're going to discuss this in detail, to be able to do the same thing for different kinds of funky data sets. And we will discuss then what creates the solutions, what produces those solutions. But that's why I started saying, do you understand where the intercepts are coming from? Do you understand how the weights of the network become the intercepts of a separating hyperplane? And how is it that you can then use it to compute linear separations between input data sets? Linear separations are very fundamental because they're really distinguishing, or they are the motors of this combination that Josh was talking about across the layers, or at least as we understand it now. Okay, I stop now at the beginning of the perceptron. Then I'm going to tell you the one problem it has, and then we're going to go into how convolutions work in a moment from now. And we're going to, so this is a part of the lecture that we're going to have sprawled in today and next Tuesday, so that we can have time to relax it. I just wanted to get this amount of information across. Do you have questions up until now? You should have interrupted too, but if you have questions now, this is a good time. And then, because it's been an hour since you've been online, I think that we can reconvene at 11:30, 11:35, if that makes sense to you. But I'm here for questions.